Hello everyone, this presentation is about gravity or gravitational force. Basically, we will be talking about what exactly is gravity, how can we define it, what are the factors which are controlling gravity, and how can we calculate gravity that exists between any two objects that you see around you. All right, so let's start with the presentation. Okay, so what exactly is gravity? Gravity, as we all know, it's the pull of the earth on any object. All right, so normally that's what comes to our mind, right? That whenever we are throwing something upward, it will always come down because of the gravitational pull. Or maybe the reason why we can stand on the ground is because gravity is always pulling us downward. So those are the basic conception that we have about gravity. But apart from this, we probably do not know that gravitational pull is something which is expanding within the entire universe, and it has a range of infinity, or it has an infinite range. And what it means is that it actually exists between any two objects that you see around you. All right. So when we are talking about the common objects that we have, maybe a pencil and an eraser, a chair and a table, they all are exerting certain amount of gravitational pull on each other. It's not that just Earth is exerting a pull on these objects, but also any two objects, they will be always influencing each other with the force of gravity. Now, your question may arise, what is the reason? Why can't we see these objects moving towards each other? Just like we see any ball or anything that you're throwing upward, it's always coming towards the ground, towards the earth. So there is an interaction happening between the earth and the ball. But why don't we see any other objects moving towards each other, which are also influencing each other with the force of gravity, right? And this is what we will be talking in detail. We will talk about the factors and everything. So you will come to know, all right? So this is called Newton's law of universal gravitation. And you can see there is an equation given here. This suggests what should be the formula or what should be the equation to calculate the force of gravity existing between any two objects having a certain mass m1 and m2, and they are spaced at a distance d apart from each other. Now you can see a capital G over here, which is basically the universal gravitational constant, and the reason we call it universal gravitational constant is because we use this value, this 6.67 times 10 to the power negative 11 Newton meter per kilogram squared. This is the value of the gravitational constant, which is applicable for any object that you see around you. It can be between two planets, it can be between even a pencil and an eraser. All right. So universal gravity is the weakest force out of all the fundamental forces that we have come across. Like any other force, maybe applied force, tension, friction, magnetic force, electrical force. Out of all those forces, gravity is the weakest. Now it depends on two things. One, the masses of the two objects which are interacting. Secondly, the distance between the two objects. So as you all can see that the gravitational force is directly proportional to the masses of the two objects involved. So if you increase the mass of any of the two objects, you will see that the gravitational force is proportionally going to increase. And if you increase masses of both objects, naturally, since it's a product in the equation, you can see that it's going to proportionally increase as the product of the two masses. By the amount that you are increasing the two masses, if you multiply that amount, that's going to increase the overall force of the gravity. So let's do an example here. Say for example, one of the mass is maybe say increased 2 times, all right? And the second mass is increased, say maybe 3 times, all right? Now, if you find out the overall force of gravity in this case now, it's going to be 3 times 2, which is going to be 6 times the original value of gravity that was existing before when the two masses were not increased. All right. If you simultaneously just increase one of the mass, just whatever amount by which you are increasing each of these masses, that is going to reflect on the overall value of the force of gravity. Now let's talk about gravitational force, how it gets affected by the distance between the two objects. Now when we are talking about interaction between Earth and any other object, we normally consider the distance from the center of the Earth to that object. Now in this case, if something is on the surface of the Earth, the distance of separation is going to be the radial distance. That means the radius of the Earth. Now you can see if the distance is 1 r, that means if it is equal to 1 times the radius of the Earth, then the force is, say, 1 g. That means, say, 1 gravitational pull. Now we are just talking about a rough estimate of how the force is going to be. Say it is 1 g. Now the moment we double the distance, you will see that the force is going to get reduced. So the more you space the objects apart from each other, the force is going to decrease. All right, and it is decreasing by a square amount. So you can see if you are increasing the distance by 2, the force reduces by 1/4. That means square of 2. 1 over square of 2, right, which is 1 over 2 square, right? Now if you are increasing the distance 3 times, the force is going to get reduced by 3 square, which is going to be now 1/9 of the original value of the force, and so on. So just remember, force is basically dependent on the inverse square law, and this is how we write it, the relation. So 1 over d squared, that's how the force varies. So as you go on increasing the distance, the force reduces by a square of the amount by which the distance is changed. So now look at this problem. Consider a pair of planets at a distance apart from each other. If their masses somehow gets doubled, by what factor does the force of gravity change between them? So you are doubling the masses. How does the force of gravity change? Now remember, as I showed you, so the masses, say there are two masses. I'm trying to draw the pictures with using my mouse. So say this is one mass, the second mass is here, okay? All right, say this is M1 and this is M2, okay? And you are doubling this mass 2 times. This is also 2 times. Now you know force is proportional to the product of the two masses. All right. So if you are doubling each one of them, it's going to be 2 times 2. So you basically multiply the factors by which you are doubling it, by which you are increasing the values, and then that is going to be 2 times 2, which is 4 times. So the overall value of the force increases 4 times. If you increase the mass, maybe say 3 times one of the masses, and the second mass maybe 5 times, the force will be increased by 3 times 5, which is 15 times. If the moon were twice as massive, would the attractive force of Earth on the moon be twice as large of the moon on Earth? Now this question says that if the moon was increased 2 times, and you are talking about moon and Earth in this case. So you have Earth here and there is a moon which is revolving around the Earth. Okay, this is Earth. Now, if you are increasing the moon 2 times, what should be the overall impact on the force existing between the Earth and the moon? So naturally, you know that the force is going to be 2 times the previous value of the force. Whatever force was there at the beginning, now it's going to be 2 times. Now remember, gravity is always a mutually attracting force. So whatever amount of force Earth is exerting on the Moon, Moon will be exerting the same amount of force on Earth. So it's also going to be 2 times the original force. All right. So even though you are just increasing the mass of the Moon, but the overall impact is going to be the same for both masses. So it's going to be, if the force increases 2 times, the amount of force that the Earth is exerting on the Moon and the Moon exerting on the Earth is going to be the same, which is going to be 2 times the original value. So if you plot the force with the distance, this is how the graph looks like. Now you know that the force is actually inversely proportional to the distance square. And that is the reason you get a curve, not a straight line. So you know that as the distance goes up, force goes down. The relation is inverse. But there is a square term over here. And because of the square term, you don't actually get a straight line, but you get a curve like this. So just remember the value. As you space them apart from each other, the more you increase the distance, less will be the amount of gravitational pull existing between the two objects. A student studies gravity using objects that have the same mass. Which two objects have the greatest gravitational force acting between them? So if you look at the two masses, you can see 100 kilograms and 100 kilograms. All of them are having the same mass, but probably different shapes and sizes. But that doesn't matter. Remember, the volume is not that we are going to consider. We will be just looking at the masses of the two objects which are interacting. In this case, just because the two masses are equal to each other, so we have to now look at the distance between them. So we can see for A, the masses are the closest, all right? So this one will be having the greatest gravitational force out of all of these other options, all right? So the greatest one is going to be A, all right? Then the next one, if you look at the distances, B and C, they are having the same distance. So we will be writing B is equal C. And then the least is going to be D, just because the distance is more. By what factor does the force of gravity between two planets change when the masses of the planets remain unchanged, but the distance between them is decreased by 5? So as you are reducing the distance by 5, naturally, you know that from inverse square law, it is inversely proportional to the square of the distance. So if you are reducing the distance by 5, that means what? We are actually changing d into d over 5. Okay. And now if you put this value, you are making the distance 1/5 of the original value. And now you put it in the denominator of the fraction. So this 5 squared, just because this 5 square is in the denominator of the denominator, we can take it up. So that will be 25 times, right? Divided by d square. So that means our force is going to be 25 times the original force. All right. So if you reduce the distance, naturally the force increases. Now this slide is to summarize the effect of mass and effect of distance on the force of gravity. You can see we are considering the original force as F, which is existing between these two objects, right? M and M. Now the moment you are increasing one of the masses, you are making it double, the overall force becomes double. If you increase both masses 2 times, the overall force increases by 4 times. If you increase one of the masses 3 times, the overall force increases 3 times. So this is basically a linear variation. Now if you look at the distance, say they are initially spaced apart at a distance d from each other, so we take the original force as F. Now the moment you are spacing them apart even more, if you are increasing the distance 2 times, the overall force will be reduced by 4 times. So it's going to be 1/4 of the original value. If you bring them closer to each other, if you reduce the distance by half, the overall force increases 4 times. And if you increase both mass and both distance, there will be no impact on the overall force. And the reason why is it so is because if you write the equation, F is proportional to, now if you write twice m times twice m, all right, and divided by 2d square, right? Now 2 times 2 is 4, divided by 2 square is also 4, so the overall impact becomes 0. So it remains the same amount of force.